My dear friends, this is Louis Chen, a teacher candidate of the MAT program at Empire State College. If you remember, in my first YouTube microteaching, I posed several questions regarding to my potato experiment at the end for my students to answer. Well, I would like to take this opportunity to address some of those questions and also share with you an inductive lab experiment that I will ask them to conduct in my class using Microsoft Excel. If you look here, you remember that the electrical potential of the potato battery was 0.62 volt at the beginning. But after the potatoes were submerged in cold water, hot water, and cold salt water for a long period, the potential became 0.52 volt, 0.40 volt, and 0.35 volt respectively, a drop of 16.1% to 43.5%. So the question I want my students to think about are, why did the electrical potential go down considerably after the potatoes were submerged in cold water, hot water, and cold salt water? In the potato or electrochemical cell experiment, which two variables were directly related to the strength of the electrical potential? Through my discussion with the students, I expect that we come up with the following observations. 1. Potatoes absorb cold and hot water because of the presence of phosphoric acid inside the food. The acid made the potatoes more concentrated and water moved into the potatoes because of osmotic pressure. It lowered the electrical potential because water in the potato was diluted. Number 2. Potato lost water in salt cold water because the outside water was more concentrated. Water moved out of the potato also due to osmotic pressure. Because of the change in water concentration, there was a drop in electrical potential. Number 3. Electrical potential dropped differently under different water temperature. As a result, we can see that the electrical potential is a function of temperature and concentration of the cell solutions. Before I ask my students to conduct the inductive lab experiments, I introduce to them the reaction quotient, Q. Q is the aqueous solution of the anions divided by the aqueous solution of the cations in an electrochemical cell. In a zinc copper electrochemical cell, Q is simply the aqueous zinc ions over the aqueous copper ions. The electrical potential is a function of temperature and reaction quotient. I set up two Microsoft Excel worksheets for my students to conduct the lab experiments. Here is the first one. A new zinc copper electrochemical cell is originally present at 298 K and at about 1 atmosphere. If the reaction quotient Q is able to maintain constantly at 300, the students are going to enter 10 appropriate temperature data points, or T, in the green area on the worksheet. Once a data point is entered, the corresponding value of electrical potential E will show up in the yellow area. I have already set up a program to calculate each E automatically once a value of T is entered. The next step for the student is to generate a graph to show the relationship between E and T. In the second worksheet, the temperature T of the electrochemical cell is set constantly at 298 K. The students are going to enter 10 appropriate data points of reaction quotient Q in the green area. Similar to the first one, a corresponding value of electropotential E will show up automatically in the yellow area once a data point of Q is entered. The next step for the student is to generate a graph to show the relationship between E and Q. The graph between E and T will look something like this, as shown on the right-hand side. The students should be aware that the value of T entered in the green area cannot be equal or higher than 511 Kelvin, the decomposition point of zinc sulfate, which is the lowest of the two cell solutions. E is inversely proportional to T on the graph. I expect the students will apply the technique of linear regression and the coefficient of determination, R squared. In this graph, r squared is 1. It shows that the line is indeed a straight line. For the graph between E and Q, it looks something like this on the right-hand side. The students should be aware that the value of Q in the green area must be above 1. The copper cations continue to diminish, and zinc anions continue to increase once the cell starts to operate. As a result, E cannot be lower than 1. The students should be aware that E and Q cannot be represented with a straight line because r squared is far away from 1. With trial and errors, I expect the student can verify that E is inversely proportional to log Q. If they apply linear regression in Excel, they are able to show that r squared is 1 and E is indeed related to log Q. After the students have finished the inductive lab experiment and each student group presented the results, I'm going to use the last few minutes of the lecture to show them the actual formulas of the Nernst equation. The equation was generated by German chemist Walter Nernst, and you can see that the relation between the three variables E, T, and Q are equivalent to what I have shown a moment ago. The Nernst equation is not one of the topics to study in region chemistry, but if the students go into AP and college chemistry, this is a fundamental equation to study in electrochemistry. As a result, I would like to show them the kind of topics they will see in advanced chemistry. Well, my dear friends, it has been my pleasure to meet you in my self-introduction and plea for chemistry, in my first microtube video, and finally in this video. I hope that I will see you again in the future. Thank you very much and have a good day.